This podcast is brought to you by LMU Munich.
Thank you so much, Stefan, for the very kind introduction and kind invitation to this place. And thank you, Hannes, for saving us with the technical innovation. And thank you, everyone, for coming to this event. It's a real pleasure to be here, especially as LMU in Munich is one of the best places for both philosophy and physics. The title of my talk today is AI Meets Philosophy of Science Towards the Foundations of Artificial Intelligence. The guiding idea here is that recent developments in AI, especially large language models, raise foundational questions that philosophers of science and scientists are well positioned to engage with. I want to emphasize at the outset that the questions I'll be raising here are not foreign to philosophy or philosophy of science or perhaps to physicists. On the contrary, they are very natural ones, issues about induction, generalization, laws of nature, chances, and simplicity. Those have been central to our discussions for a long time. And in philosophy literature, they started much earlier, but we have seen discussions in Hume and to Goodman and well beyond. So what's new here today in this discussion is not the questions themselves, but the empirical context in which they arise. So modern AI gives us a new kind of evidence and a new testing ground for ideas that philosophers have been developing for decades in the context of scientific theories, such as those in physics. And because of the pace of recent progress in AI, this talk is motivated by a sense of urgency. AI is advancing so rapidly, and yet we still lack a clear theoretical understanding of why the systems generalize as well as they do, or what the success tells us about the nature and the structure of the world we live in. For that reason, my talk today will be painted with somewhat broad brushstrokes rather than fine technical detail. So this will be a programmatic talk. My aim is to lay out a possibly coherent framework for thinking about a set of issues, show how this connects to a range of phenomena, and highlight some open questions. I'll be very happy to slow down and discuss details in Q&A. More generally, I want this talk to serve as an invitation to us here in philosophy and in physics to get involved in this new interdisciplinary sub-area continues to take shape. Okay. There's a handout, by the way, with a few highlights and definitions and summaries and some references, but most things will be on the slides. Okay, let me see if it works. There are two mysteries of nature that are really puzzling to me, and perhaps to you as well. The first is that the laws of nature, the ones we have hypothesized and tested and discovered and evaluated, the laws of nature in physics and other disciplines are surprisingly simple. In the best case, maybe they can even fit in on the t-shirt. And the second mystery is that AI works so well, better than anyone predicted, better than anything that make them happen so well that we have theoretical reason to believe in. My hypothesis in this talk is that the two mysteries are in fact linked, that the simple laws of nature make it possible for AI to work so well, and on the other side, the success of AI provides concrete evidence for the kinds of simple laws that we have in the world. And I think this prompts time for a new field, which we might call foundations of artificial intelligence. Let's start with some recent successes of AI. We don't have to go through each one case by case because you've seen the headlines that the successes just in the last few years, last few months in science, in mathematics, in language, in creative tasks. And my favorite is the practical tasks now, that you don't have to worry about being scammed for home improvement projects. You just take a picture and ask a large language model about whether this is worth thousands of dollars spent on this task. So they display generalization far beyond training data they've seen during training. And their successes seem to surpass many depictions in science fiction. Think about HAL in Space Odyssey, and even Turing's 1950 vision of machine intelligence that passes the Turing test. Just a few hours ago, OpenAI released a blog post with a paper and summary of comments from field medalists and other mathematicians that they had an internal model like ChatGPT, but the one they have access to, probably larger and more expensive to run, that resolved one of the open problems in discrete geometry, the unit distance conjecture. It was actually false. We disproved this. And this will be submitted to, say, Annals of Mathematics, the leading journals in math. It will be accepted without hesitation, according to Timothy Gowers, if he were the referee for this paper. So it is a mainstream mathematics research open problem that has been solved by an AI model. In particular, it's a large language model, not trained particularly for mathematics. And this is especially striking because just 10 months ago, the model of ChatGPT were about to solve math problems in International Math Olympiads for the high school math problems, and they achieved gold medal performance. But 10 months later, they were solving research-level mathematics problem in the frontier. Despite all the success, yet we don't fully understand why AI works. There's a famous quote from Ali Rahimi that says, "Machine learning has become alchemy." This was at the NeurIPS 2017 Test of Time Award, as one of the largest AI conferences. And this is even before large language models. So things have become much worse with large language models because machine learning has become even more like alchemy by trials and errors and not really by first principles, guarantees, theoretical reasons that we understand. So the point is that the practice of machine learning, building AI models, far outruns understanding. There is a crisis in machine learning, ML, that is, there is no satisfactory theory of generalization, or we philosophers sometimes call induction. There is no adequate explanation for AI success. So at this point, you might wonder, do we even need an explanation? It works so well. It is so powerful. So Yang Laquan's reaction to Rahimi's talk was that, well, the search for explanations, theoretical guarantees, is akin to looking for your lost car keys under the streetlight, knowing you lost them someplace else. There's a streetlight effect. The first response is that it is a good point. You probably want to use a flashlight or on your iPhone, just kind of go with you, not a very strict and inflexible streetlight. But the second response is that yet we still need an explanation in the case of AI success, even without sharp inequality bounds, even without theoretical guarantees. We want to go some steps towards understanding how they work and why they work so well. Why is that? Well, for safety, understanding, and predicting future model behavior. One of the recent posts from the company Anthropic was something called personality selection model. It is a somewhat speculative theory of psychology of large language models. It's not just trying to think, okay, how close it is to human, but to understand how can we make predictions about, say, cloud behavior in different situations by borrowing ideas of human psychology. It is trying to construct a theory of LLM mind or theory of LLM generalization to predict what's going to happen when you have LLM different circumstances that we haven't seen in training. So what might an explanation look like? There's a traditional way of thinking about the problem that's called the curse of dimensionality. That's where we shall start. The problem of learning in general is that in high-dimensional spaces with many possible data in the world, learning is generically nearly impossible. It's very, very hard. The standard response is that, well, in the actual world, something like the manifold hypothesis is true. Roughly speaking, it says data from the world, either images, videos, or texts, or properties you sample from the real living systems, they live on a low-dimensional manifold. And it's the low-dimensional manifold we're interested in recover using learning. And from this is the kernel of generalization for things we haven't seen in training. So the manifold hypothesis is a core and a useful gloss on this response. It is basically a version of Occam's razor, preference for simplicity, preference for, think that nature is very simple. It is in the right direction, but conceptually it is ambiguous. It may ask different kind of questions. How low is low? How many dimensions? And which coordinate system is this low-dimensional manifold that generalizes to other situations? And this is something related to feature learning and concept learning. And 3, and more concretely for physically, what does the low-dimensional manifold represent as a physical process, physical state, physical system, or physical description? What is a concrete physical thing we can think about in terms of the manifold? It's not just a mathematical thing. It's something implemented in nature that generates data for us to see and discover. And thinking about dimension, the curse of dimensionality, is helpful to think about this more concretely. So here I'm going to use an analogy from a collaborator and friend, Mikhail Belkin. It's a vast library. So imagine there's a vast library of, say, 5 billion books, right? Huge. A certain book in the library has a certain letter in a particular location. Within that letter, there's a molecule of ink. So there's a letter G, and within that letter, the printing of the letter, there's some ink molecule. Let's call this Alice. The goal is to reconstruct all books in the library, 5 billion books and contents, from Alice, the one molecule in this letter on this book. Now, while this task may seem absurd, it pales in comparison to the problem we are facing. Which problem are we facing? The problem of learning patterns from data, even in large models like large language models. The data we have from the internet, say, all of the internet, plus Reddit and JSTOR and Archive and Wikipedia, maybe even more, has around 100 trillion tokens, 10 to the 14 tokens. It's huge by our standard. But even if we ask a simple question to a large language model in ChatGPT in the context of, say, 300 words, which is about 1,000 tokens. And even for a smallest model with 1,000 many vocabulary, different words, you can use different tokens, that alone has 1,000 to the power 1,000 possibilities. So there's this many ways to answer the question. And this number is huge. It is bigger than 10 to the 80, which is the number of known particles in the known universe, and that's much bigger than 10 to the 14. So the dimension reduction achieved by modern AI, such as large language models, is staggering. It can go from this few tokens to this many possibilities and finding the right path, right solution, right answers in a meaningful way. And this should be surprising to everyone. And it was not predicted by any theory of learning before large language models or before deep learning. We need a systematic theory of learning in the physical universe. The central question I want to address today is this. What must the world be like for learning to work at all? Not just data, not just algorithms or architectures, but what must the world be like for learning to work at all? Because in the end, we're learning things and doing things, generalizing about things in the world. And this is where AI meets philosophy of science. It is, I think, a surprisingly fruitful yet underexplored connection. At their intersection lies the opportunity for a new field, which we might call foundations of artificial intelligence, which could be similar to foundations of physics, clarifying the conceptual issues in quantum mechanics, system mechanics, general relativity, and field theories, or foundation mathematics, understanding the consistency and the theory underlying all branches of math, or foundation for probability. How does probability hook up to the real world? And this could be a cross-disciplinary domain for fundamental questions raised by AI about the nature of mind, language, and even the world itself. So I want to discuss some of the themes in this talk, and focusing on the question is, okay, what must the world be like for learning to work at all? My plan for this talk, I've discussed the puzzle of learning, which is impossible but somehow very efficient for learning systems we have constructed. And for us, for humans, we have done this for thousands of years, billions, hundreds of years as we construct scientific theories. But for machine learning models, it's kind of a different kind of puzzle. It becomes much more crisp because the machines have known objectives, architectures, and data. The proposal I want to discuss involves laws of nature. I'll discuss some evidence in support of this proposal and the limits to learning in light of the proposal. and implications for both philosophy and for AI. So the first step is just put on our philosophical lenses, conceptual lenses that will be updated in the modern regime. So there are the problems of induction in philosophy, and they can be updated to the modern case. There is a problem identified by David Hume in 1700. He suggests that there is no non-circular way to justify induction. You have to start by assuming something, that nature is somewhat uniform or simple in some way, such that learning about things from the past or from this area can generalize to things in the future and to other areas. The basic idea here is that many hypotheses are compatible logically with data we have, which is finite, macroscopic, coarse-grained. Why should we prefer the uniform ones over any ones compatible with the data? Think about two hypotheses: the sun will rise tomorrow versus the sun will explode tomorrow. Both are compatible with past observations. The sun has risen every day in the past. And yet one is, in some sense, intuitively simpler and more uniform, continuation, the same pattern. And the other, the sun will explode tomorrow, has this discontinuous or big change, and that's somewhat non-uniform and dispreferred. There is no a priori method to decide between the two based on logic or probability theory alone. In machine learning, there's a similar no free lunch theorem that says no a priori method generalizes from data in all cases. So we have no a priori way to justify induction. It must be from something else we hypothesize or assume. Related to Hume's problem induction, in the 20th century, we discovered there's a second problem, the new riddle of induction by Nelson Goodman. In the 50s, Goodman realized that even if you assume this uniformity of nature holds, in some way with caveats, the concept of uniformity itself is ambiguous. If I grant you are allowed to assume uniform pattern in nature, if you observe that all emeralds in the past are green, you have two hypotheses to generalize to. One is all emeralds are green, period. And the other one is all emeralds are GRU, where GRU applies to green emeralds prior to time t, and blue emeralds after time t. T is time of discovery. So both are uniform hypotheses compatible with past observations of the colors of emeralds, and yet one generalizes to the next one will be green, and the other one generalizes to the next one being the blue. And which one to decide? There is no a priori method to decide between the two. So philosophers sometimes invoke natural properties or some kind of projectable concepts. In machine learning, there's a similar kind of problem. That is, there is no a priori choice of representational space or feature space, the space of concepts, the kind of x-y axis you write down before writing down the manifold. So both problems of induction show up in a modern case of developing machines that can do prediction. And both are difficult because there are no a priori answers. We have to rely on something, empirical or substantive. Let's think about Hume's problem for a second. The standard response to Hume's problem is Occam's razor, preference for simplicity. And the manifold hypothesis is assume data comes from a low-dimensional manifold. So the slogan is that other things being equal, you should prefer simpler theories, regularities, or truths. So something like this could work for a slightly more precise version called the principle of simplicity. Other things being equal, simple propositions or simpler equations are more likely to be true. More precisely, other things being equal, you have two equations, so two propositions, L1 and L2. If L1 is simpler than L2, say L1 says F equals MA, L2 is a big, long conjunctive equation, both are compatible with the data, then you should assign higher epistemic probability in L1 than in L2 being true. So the greater than P is probability assignment, and greater than S is a simplicity judgment. Now, of course, you can build in more to simplicity. You can have other things like strength and elegance alongside with simplicity, have overall comparisons. But anyway, this is kind of the schema for using simplicity as a super empirical tiebreaker when you have hypotheses or theories or truth that are both compatible with some data. It is plausible and intuitive, but it cannot possibly be true. It is probabilistically incoherent as a universal principle. And it was first raised by Karl Popper in the 70s against Winch and Jeffrey's account of scientific inference developed in the early 20th century. And it was recently discussed by Eddie Sober, Jonas Schubeck, and Leo Henderson in the recent philosophy literature. So here's a version of the problem that's kind of simple to explain, which is a problem of nested theories, sometimes called the problem of conjunctive explanations. Consider two theories of nested sets of models, L1, L2. And L1 suppose is simpler than L2, and yet L1 entails L2 logically. So in this case, every model of L1 is a model of L2 and not vice versa. Now, here's just a consequence of probability calculus, the monotonicity of probability. The probability L1 is true cannot be higher than the probability L2 is true. And yet that's what the principle of simplicity recommends against. So the principle of simplicity is incompatible with the simple observation about monotonicity of probability. So think about L1 being, say, Einstein equations compatible with space-time with general relativity, and L2 being, say, Einstein equation with disjunction, with union with something else, with kind of a bunch of ugly spacetimes that are very complicated to describe. Then L2, even though it's more complicated, cannot be less likely to be true than L1, just because L2 is a superset of L1 in terms of set of models. So the first step we should do is to try to repair the outcomes razor. And the repairment is what I call the gnomic razor. Gnomic here means nomological, or to do with laws of nature. The razor for laws, not razor for truth in general. So simplicity here should be regarded as an epistemic guide to discovering laws of nature, not a general guide to truth. So here's the slightly more precise version. Other things being equal, if you have two propositions, L1 and L2, if L1 is simpler than L2, then you should assign not L1, but the proposition that L1 is a law, higher prior probability than the proposition that L2 is a law. So the LL1 is the sentence that L1 is a law of nature. So for example, think of L1 as the equation F equals ma. It is a truth, it is a falsity. By other way, it's something concrete. And LL1 is something a bit more abstract, something more robust about related to causation and counterfactuals and possibilities. So LL1 in this case would say F equals ma is a law of nature, which implies the physical possibilities are given by F equals ma and beyond. So the basic idea is that simple candidate equations or simple candidate functions, simple candidate principles get higher credence as laws of nature. It doesn't require the simple candidate regularity to be more probable to be true. And this is compatible even assuming that lawhood entails truth. Suppose you believe, as I do, as humans do and some non-humans do too, that something being a law entails something being true. This is still compatible with this principle because what likely to be a law does not entail what likely to be true. It sounds like tongue twisters. So here me give you one picture of model. So it can have L1 be nested within L2. And yet LL1 is not nested within LL2. So LL1 is a proposition that entails L1. LL2 is a proposition that entails L2. So LL1 has bigger area than LL2. And yet L1 can have smaller area than L2. And this is how you can say coherently, L1 has lower probability than L2. And yet L1 being a law can be more likely to true than L2 being a law. Okay, so this solves this nested theory problem. It aligns with our theoretical considerations about induction, underdetermination, symmetries, determinism, and explanation. So I argue in this recent paper in News called The Simplicity of Physical Laws. So it's kind of was a package of theoretical fruits I think are attractive of thinking about simplicity as tracking lawhood, not truth simplicator. So on this picture, lawhood can entail truth. There's no separation between lawhood and truth. It's just that lawhood is stronger than truth. So at this step, you might ask, what is a law of nature? The proposed framework I want to discuss has three components. The first component is a account of laws of physics, fundamental laws of nature, called minimal primitivism. And the second and third components are more newer developments. They're motivated in light of machine learning and AI success. So let me start with the old news of minimal primitivism, MIMP, and go to the more recent versions. By the way, I'm here using MIMP as a concrete example, but you can substitute for a favorite theory of lawhood. Even humanism or non-humanism is fine. MIMP is a non-human account of governing laws. So the account of laws of nature applied to fundamental physics, to basic laws of nature, MIMP, which I favor, is developed with Sheldon Goldstein, a metaphysicist at Rutgers University. So on MIMP, we say that fundamental laws of nature are certain primitive facts about the world, the basic ingredients of the world. There's no restriction on the form of fundamental laws. They can be constraint laws, time evolution laws. They can be even stochastic chance laws. They govern the behavior of material objects by constraining the physical possibilities. Think of Einstein equation, give you a set of models. F equals ma, give you another set of models. So this is kind of pretty flexible about the form of fundamental laws of nature. So how do we even get to recognize the laws if we find them in the world? The second part is epistemic thesis, epistemic guides. Even though theoretical virtues like simplicity, informativeness, fit, and naturalness are not metaphysically constitutive of fundamental laws, there are still good epistemic guides for discovering and evaluating them. So the principle of nomic simplicity, nomic razor, is one kind of epistemic guides here. Okay, this is in our 2020 Pew paper, with Sheldon Goldstein on MIMP, and developed a bit more in detail in this book on laws of physics, published 2 years ago by Cambridge. And in recent work, I've been exploring with Emily Edlin how this account connects to scientific explanations. How do constraints connect to explanations? Whether we have to explain by causation, or whether constraint can explain without causal explanations. And a different line, we think about probabilities are different from pure constraints because probabilities allow anything, just assign different numbers on the different histories. So with Jeffrey Barrett, we have published a paper coming out in BJPS suggesting we can reformulate probabilistic laws of nature as constraint laws using the resources of multi-law randomness. In a recent paper on arXiv, we show that this kind of laws, probabilistic laws and chances, lead very naturally to a non-circular proof of the principle, why chance must defer to credence. And with a grad student at UC Irvine, Josiah Lopez-Wild, Jeff and I were discussing and preparing this paper for applying this framework of constraint, probabilities, randomness to quantum mechanics. So there's a kind of a expansion in the case of physical laws, an expansion of the theoretical role it plays in a scientific account of the physical world. But I want to today focus on a different kind of expansion, a different direction of expansion that's not particularly about just physical laws. I want to call the second part nomic liberalism. On nomic liberalism, laws can be simple, predictive, representation relative, and they can be at many scales, not just fundamental, and they can exist in many domains, not just in physics. And they can exist in many forms, not just our favorite concepts and coordinates, but they can exist on things much more like GRU and BLINK, and less like green and blue. That's why we might call them alien coordinates. And yet, this account of laws, this expansion of the possibilities of possible laws of nature, doesn't predict ML success, doesn't predict the success of large language models. It just makes it possible. It accommodates them. So the third part of the framework I want to discuss is nomic abundance. This is a thesis about actuality, the actual world. Not just about possibilities, but about what is actually happening in the world we live in. So nomic liberalism says laws could exist at many scales. Nomic abundance says they actually do. The actual world contains abundant, simple, generalizable laws at many scales and domains with common structures across domains, such as we can do transfer learning, such as learning about mathematics and physics can improve ability to code and vice versa. And often, those abundant laws can exist in alien coordinates, not completely legible or intuitive to human intuition. So this is an empirical claim. It requires evidence. And that's where AI comes in. Now, at this point, I want to ask kind of a conceptual question. Why are we talking about laws, not just regularities? The technical reason is that the nested theory problem suggests the connection between simplicity and induction is much tighter to laws than to mere truth or mere regularities. Naive outcome, that simpler is more likely to be true, is incoherent. And nomenclature, that simpler means more likely to be a law, restores probabilistic coherence as a chance of being true. Conceptual reasons, these are familiar to people who have thought about counterfactuals and laws. Generalization requires projectability, and mere regularities don't support projection beyond observed data. That there are 5 coins in my pocket doesn't predict anything about your pocket or my pocket tomorrow. Laws do. And the second is that explanation. Something being true does not explain that being true. Laws do. That P is a law explains P and the phenomena associated with it by providing simple, informative logical consequences. Okay. I think of AI as controlled experiment in this context for the following reasons. It provides controlled experiments on learning because AI models have known training data, at least in principle can go through them one by one. It's an enormous task, but at least it's in principle scrutable. It has known objectives. It has known objectives that are sometimes very simple, sometimes a bit more complex. And you have known observable structured discovery. You can verify, you can test, you can have results at the end of prediction. Is it true or false? Is it classifying correctly? Or is it making predictions that are closer to the ground truth? So AI success is evidence about worldly structure. In this light, AI is not just an engineering achievement. It is not we just have data and compute and put it together and it works. It is actually a scientific milestone, revealing something about the world and how we think about the world. There are 3 lines of evidence I want to discuss in support of this nomic abundance thesis. The first evidence is double descent. Second, scaling laws. And the third and most controversial piece of evidence is the emergence of artificial general intelligence, or AGI. The first piece of evidence is double descent. So on the left, we have this traditional bias variance curve in statistical learning. We've learned from statistics and many ways of doing data testing that you don't want to have underfitting and you don't want to have overfitting. If model underfits with too few parameters, you might miss the signal in the data. If you have too many parameters in the model, you might overfit the noises. So you won't generalize well in either case. So somewhere in the middle, you should find a sweet spot. And that's the spot that actualizes this bias variance trade-off that has the best performance on unseen data. And that's the traditional wisdom. Turns out to be incomplete or actually incorrect. In the modern machine learning regime, where you have big models and bigger models, we are really in the regime of overfitting. And in this case, we can parameterize, we have more parameters than data points. Turns out it's not going to get worse, but it's going to get better. And this is from Mikhail Belkin's tutorial paper, Fit Without Fear. So this kind of shows up in a variety of cases, a variety of data domains, a variety of architectures. And in this case, you have bigger and bigger models, you have more parameters, you actually can improve the performance on new things you haven't seen in training. And in some cases, you can prove analytically this is going to be better than even the first trade-off point. Okay, this is called double descent. The second descent is where it's surprising. What it's telling us is that past interpolation threshold, where the threshold where we have as many parameters as data points, we enter into a regime where many functions fit training data perfectly. You have no loss empirically. You make no mistakes on the things you have seen in training. And training dynamics selects among perfect empirical fits, gradient descent, stochastic gradient descent. The selection criterion is something like you select a function that's minimizing the Hilbert space norm in the function class you are allowed to choose from. And this is kind of an implicit way to think about simplicity. So the philosophical upshot here is that simplicity in this case is not just counting parameters, how many parameters the model has, which was the foundation for classical heuristics. But it's representation dependent, in the sense that you think about the function that the model realizes, and the implicit bias, if it is coherent probabilistically, should implement something like the nomic razor, looking for causal or explanatory or lawful hypothesis that's simpler. The second kind of evidence is scaling laws. And this was discovered about 10 years ago, and one of the most famous papers is this Kaplan and company paper in 2020 about neural scaling laws. So it turns out that there are really predictable and simple behavior when you scale up things. And this is the foundation of investment in AI, because if you do this for some smaller models, you know if you invest in more money, and by scaling up in some way, you can get better performance. So it's not just kind of academic exercise, it is leading people's decisions on where, how, and how much to invest. So what people found is that if you increase compute or GPUs, you get lower loss. If you have more data and you have more parameters, and the three are synchronized in some way, then they lead to lower loss systematically. And you have this power law phenomenon you plot on the log scale is linear, it's smooth and simple predictable. So it's a predictable way of improving performance. And it's remarkably robust across domains and architectures, with a caveat that the exact mathematical form may not be so simple as a power law. It might be something else that's going on in practice we don't quite have access to. So even granting that mathematical form is more complicated in practice, it is something that is still simple enough to understand on the heuristic level. And there's another scaling law that was recently discovered a few years ago, and was also shown in the recent paper by Anthropic that's called test time compute scaling law. That if you allow, it's just like during training, bigger models and so on, and more data, you can also scale up inference time, thinking time, how many steps, how many tokens, how many energy uses for thinking. And that can also give you predictable way of a power law relation between scaling and performance. So there are two lessons I want to draw from scaling laws phenomenon. One is epistemological and one metaphysical. On the epistemological side, scaling laws are themselves laws of learning. Induction in those domains is stable, and the pattern of the induction is pretty predictable. On the metaphysical side, insofar as those things pertain to actual things in the world, in natural data or even synthetic data, it turns out that the world contains abundant lawful structure at many scales, and they can be progressively revealed to us by more powerful learners, better system or systems. So on both sides, I think that there's this connection between scaling laws phenomenon and our thinking about laws. And the third piece of evidence is the most recent one, is the emergence of AGI. And this is arguably the most controversial piece of evidence, so it requires some setup and arguments. It'll be theory-laden. With large language models, we've seen in the last 7 years or so, the training objective is basically the same. It's predict the next token based on previous tokens. And now we have models such as GPT 5.5, Claude Opus 4.7, Gemini 3.1 Pro. And the result is that they have achieved general capabilities comparable to human intelligence across many domains. Frontier large language models are artificial general intelligence, or AGI. Now, the case for AGI is best made in the context of Turing's vision for machine intelligence. In 1950, about 75 years ago, Alan Turing published a paper in the philosophy journal Mind, which is still one of the best journals, on computing machinery and intelligence. And he asked a purely hypothetical question back then. The question where, you have giant computers that can do things that are great, but not as general as even computers we have on the laptops right now. He asked a question, can machines think? Be one day, when they develop powerful enough, can they think? For Turing, the question of thinking is too vague. He suggests we replace this question with something operational called the imitation game. Can you tell, are we conversing in text messages with a machine or with the actual human. And Turing's vision was realized and exceeded. Last year, in March, large language models reliably passed the Turing test. My colleagues Cameron Jones and Benjamin Bergen at UC San Diego, they did this test on undergraduate students and people online, and also with ChatGPT and other models to see if the Turing test was indeed passed. It turns out it was exceeded. When prompted to adopt a human-like persona, one that can use slurs and jargon and other things, GPT 4.5 was judged to be human 73% of the time. Significantly more often than interrogators selected a real human participant, which is 27% of the time. And I have students who were in that study and they told me it was actually hard. You were in that study and trying to ask questions about what you are seeing, what you experience, what you have for lunch, and so on. It was hard to recognize what is human, what is machine. Anyway, so this is done last year, and there's different versions of this test being done, not just for text messages, but also for writing tests and so on. The Turing test is far from the only evidence. Just last year alone, we've seen gold medal performance in international competitions by large language models in the Math Olympiad, Physics Olympiad, Astrophysics Olympiad, I think Bio Olympiad, and coding competitions, cybersecurity competitions. All of them just have the frontier models, Ace, gold, top level. And they've also participated in frontier research in multiple fields. In physics, for example, some particle physicists use them in their own research and try to replicate it. Can they do this experiment? Or can they do this calculation and prove that get to this result I've secretly been doing for several months? And it turns out they can. And the recent example from math was, suggested by Fields medalists saying that this can pass referee review at top journals of mathematics, solving open major problems in mathematics. And they've also been shown to surpass experts in several knowledge work tasks, including creative writing, cybersecurity, and software development. So with colleagues at UC San Diego, Michael Belkin in data science, Leon Bergen in linguistics, David Angst in data science and philosophy, who has since moved to Virginia, that we argue that AGI has indeed arrived. Current LLMs fulfill and exceed Turing's 1950 vision of machine intelligence, i.e. AGI, though Turing did not use the term. General intelligence is about having sufficient breadth and depth of cognitive abilities, characteristic of human thought. Recognizing that this is kind of vague and fuzzy, we think that most, if not all humans, individual humans, are general intelligence. And in that case, we draw the conclusion that insofar as individual humans are general intelligence, LLMs are too. And it was published in Nature about 2 months ago. So why should this work at all? We thought those domains mastered by LLMs were hugely complex. Math, physics, coding, language, home improvement advice, and trip planning, and possibly unrelated. And they require distinct expertise. That's why people trained lots of special AI models before they tried this LM thing that they found maybe we should do narrow intelligence first before getting general intelligence. But no, this case is this completely emergent intelligence from different domains from a simple objective. And those domains seem to have astronomically large space of possibilities. Recall the vast library. So the vast library is better than most of the problem we ask LLMs. And yet one learning rule, pretext token, one kind of data, text data primarily, you have achieved competence across all. The emergence of general capabilities from next token prediction is evidence of abundant cross-domain structures, which we might call laws. So we say in the paper, in 1965, reviewing AI progress for the RAND Corporation, the philosopher who was at UC Berkeley for many years, Hubert Dreyfus, he compared AI research to trying to reach the moon by climbing a tree. The point is that it's impossible. So Dreyfus is a well-known AI critic. For decades, this seemed right. But as the evidence mounts, it is increasingly clear we misjudged the nature of the moon and the power of the tree. General intelligence can indeed emerge from simple learning rules applied at scale to patterns latent in human language, patterns rich enough, it turns out, to encode much of structured reality itself. So what nomic abundance explains for this picture is this: that human domains share underlying compressible structure, language encodes enough information, and simple learning rules have to extract it. And the structure may be in alien coordinate systems. So speaking of laws in alien coordinates, so we might ask, what do LLMs or similar systems actually learn after training and as they predict? So the evidence from mechanistic interpretability and AI safety research suggests that they don't quite learn the same way we do. They don't quite have the same concepts as we do. It turns out that there are many ways they encode concepts that are somewhat weird to us or somewhat alien to us. Now, this is not quite fully resolved whether this alien feature is a fundamental features of large language models or machine learning in general or the world. But nomic liberalism allows this possibility that laws can indeed exist in any coordinate system that make them simple, including alien ones. If nature decides to write down her laws in terms of alien coordinates that somewhat gruesome to us, somewhat alien to us, we don't have to complain. We can accept that we are not, the best at finding joints in nature. I mean, we're somewhat not best anyways, because think about the categories we find in quantum physics, quantum field theory, general relativity. The concepts are already somewhat foreign to most people, right? It's only after enough experience with them that we start to get some intuitions. So the concepts we have in science in general can be quite alien to people in the past. Similarly, concepts that machines discover in their training, and insofar they predict well, could be joints in nature that just we don't have good intuitions for. So let me come back to the manifold hypothesis. The standard machine learning explanation is that high-dimensional data lies on low-dimensional manifolds that enables learning efficiently given finite data. This may have worked for certain ImageNet era success, but LLM suggests the manifold is wilder and bigger. We don't quite know the manifold for language or reasoning. We don't know the coordinate system for this manifold. So on the nomic liberalism side, we can allow that relevant coordinate system may be alien to us, not human legible. And on the nomic abundance side, which is the final piece of the proposal, is that alien laws are indeed abundant. And that's, I think, supported by the considerations of this kind of evidence. On the alien manifold hypothesis, the relevant manifolds that machines discover may employ concepts and features alien from human perspectives. This connects to safety and alignment. If models encode structures in alien coordinate systems, interpretability requires understanding the geometry of those concepts and manifolds. And so we can do certain experiments empirically, like neuroscientific surgical interventions, to probe both the base model and the fine-tuned post-train models to understand the nature of LLM minds. And this is something that can already do with open source models and with techniques people have discovered recently. Now, let me end with the last part, which is that abundance has limits. If the world is so learnable, why doesn't learning always work? The answer is that sometimes, one reason is that there are, in principle, physical constraints or physical laws on what can be learned. And one example that's kind of striking for us is discovered that with Roger Timolka in the recent work is what we call observation typicality. And it's one case of quantum state learning about a particular physical system in which scaling will not help and learning is, in some sense, in principle, impossible. So a complete theory of induction, of generalization, must explain both that why learning works so well in some cases, abundance, and why learning sometimes fails, the constraint. So let me introduce the in-principle limits on quantum learning. In high-dimensional quantum systems, it turns out nearly all quantum states are observationally indistinguishable. No measurement, local, global, small, big, coarse-grained, fine-grained, no measurement whatsoever can reliably distinguish those quantum states. And unless the observation is extremely unlikely, very, very, very chance, very, very unlikely, not even unreliably. So this gives you a Bayesian interpretation of this result, that if you have a Bayesian prior that's somewhat uniform over the space of possible quantum states, say compatible with some past hypothesis or other initial conditions, unless the observation is very, very unlikely, the update by conditionalization will not move the distribution much. The posterior on any observation will still be nearly uniform. So you learn almost nothing. This is in principle, not technological, not something that can be improved by better technology, machine learning algorithms, or new ideas, as long as quantum mechanics holds. So the concrete application is that quantum state learning or quantum tomography cannot scale above 30 qubits or so with, say, one or a few copies. Of course, you have infinitely many copies, it can help a lot. But for the universe as a whole, or a big system, or for a system that cannot be replicated to beyond a few copies, this kind of gives you an in-principle limitation on learning. On the flip side, this gives you kind of advantages of learning because you don't really need to know the precise quantum states, the pure state wave functions. The ensemble average is good enough for making predictions for any observations. So, by the way, I know some of you are going to UC Irvine for the Foundations Physics Conference. The weekend after that, we have a conference at UC San Diego on quantum learning based quantum foundations. So welcome to come, drop me an email. So the other side of the story is this, that in some cases, we have most of the state space is completely opaque. So to learn anything at all, it must be a very special structure, or structure pertaining to the whole state space. And we really want a principal theory induction that explains both success and failure. And this kind of revisits the question of the curse of dimensionality. Is it really a curse, or is it really a blessing? In the quantum case, it's both a curse and a blessing, depending on how you look at it. In the machine learning case, sometimes it's also kind of both a curse and blessing. It's quite interesting that how should we think of dimensionality here is a subtle story that we haven't quite properly understood in full generality. So what we learn for philosophy in this case study is the following. That first, we need to update our heuristics. Modern over-parameterized regime matters. Classical overfitting intuitions are at best incomplete. The nomic razor is a coherent, outcome-like simplicity principle. It solves the nested theory problem. So when we think about simplicity in the context of scientific discoveries and inference, we should think of simplicity linked not to mere truth, which is what we usually say, but to something more robust, like laws, causes, chances, and explanations. And for laws of nature, on this view, multi-scale laws, multi-domain laws become required. We should not think that laws are very elite, only existing in some domains, at some levels. No, this kind of really compelling kind of evidence that laws exist almost anywhere we look. And the new evidence comes from AI, as it provides control experiments bearing on the conceptual questions, the epistemology and the metaphysics of laws of nature. What we learn for AI is that I think explanations about what kind of world makes ML success possible is a fruitful foundational question. For interpretability, we should contemplate the possibility of alien laws. And for scaling, we should think that scaling success tells us something about the worldly structure that we have somewhat missed in traditional way of thinking. There were scaling laws in physics, but it turns out scaling laws are quite universal, and scaling laws are quite interesting and useful for engineering and for practice. As scaling laws could be another way to think about intelligence, think about how evolution produced us. And we can now have a different model of thinking how general intelligence emerged from training and data and compute, and think of ourselves as the realization of this scaling by billions of years of evolution. So we need to ask clear questions about AGI, simplicity, generalization, and build towards a systematic theory of AI foundations. Towards foundations of AI, I think this could be a fruitful and new field for cross-disciplinary collaboration. And some people are already working on these fields for foundation machine learning, induction, and we should engage with empirical work on AI interpretability, AI safety, and also engage with AI theory, about theories of generalization. As before LM, and now we are developing as LMs develop. And we should engage with philosophy. Traditional questions from theoretical and history philosophy really bear on these questions we have been thinking about for decades and maybe hundreds of years in philosophy of science. Okay, let me summarize. The puzzle was the AI success was a mystery, it's an explanatory challenge. The proposed explanation is to invoke laws of nature and posit that laws can be flexible in form and they exist in abundant volumes in this world. And the evidence we consider were from double descent, scaling laws, and the emergence of AGI. And we've seen one kind of limits, and one example is quantum observation typicality. The upshot is that a theory of induction must explain both success and failure. And I hope this can be an invitation that someone may be excited and interested here that we can build towards a foundations of AI. Okay, thank you for your attention.
Thanks very much.